Hi, I'm Fernando Pereira from the Federal University of Minas Gerais in Brazil, and today we shall talk about a register location algorithm called linear scan. Linear scan is based on the coloring of a class of graphs called interval graphs. In a way, the algorithm picks up a program and derives such a graph from this program. Coloring this kind of graphs is easy. There are optimal algorithms that run in linear time that color interval graphs. But the approximation itself is not optimal, meaning that the optimal coloring of the interval graph does not necessarily give us an optimal allocation of the program. It just gives us some valid allocation. As an example, consider this program. We start by linearizing it. To linearize the program, we can pile up its basic blocks. A good way to sort these basic blocks is using a reverse pulse ordering of the control flow graph of the program. Then, from this linearization, we derive the interval graph. Each live range gives us a line. This line starts in the first program point, where the variable is alive, and ends at the last program point, where the variable is alive. There is an example in this figure. Notice that this lines gives us a graph. Two variables whose lines are juxtaposed vertically cannot be assigned to the same register. Thus, there must be an edge between them. But we do not need this graph to run register location via linear scan. The intervals themselves will do. Here's the algorithm. This pseudocode was taken from the paper by Plato and Sarkar that introduced the notion of linear scan. You can take a look into the code. We will talk about each part of it soon. This algorithm uses a data structure, a list that we call the list of active intervals. The idea of this algorithm is to traverse the lines from top to bottom with a scan. Whenever we find a new line, we put it in the list of active intervals. Whenever that line ends, we remove it. To remove a line, we use this routine: expire old intervals. Whenever the scanning line goes past any line in the active set, we remove it and return the register that was used in that interval to the list of free registers. If we need to assign a register to an interval, that is, to a variable, we might have to spill some other variable. To decide which variable to spill, we use Belay's algorithm. This was an algorithm used to replace virtual pages in an operating system. The idea is to replace the page that would be used the farthest in the future. In the case of register location, we'll spill the variable that has the farthest use in the linearization of the program. Here I have a detailed example of allocation. Instead of going over each box with you, I suggest you to stop the video and read the captions of the figures. The red line is our scanning line. Next to each figure, there is a description of what happens at that point. Here I'm showing you the first 4 events performed by linear scan allocation. Notice that we will have to spill in the 4th figure. We chose to spill variable c in this example because it has the farthest use. And in this figure, I show you the next 4 events. Again, I suggest you to stop the video and read the captions under each figure. Notice how we assign registers to variables once the scanning line reaches that variable's interval. And notice how we return registers to the list of free registers once the scanning line goes past some interval. When we spill a variable, we are modifying the interval associated with that variable. The original description of the algorithm uses a very simple approach. We replace the interval with micro-intervals, one for each use of the variable yet to be visited by the scanning line. This approach is called spill everywhere meaning that we do not recycle the same load for several uses of a single variable. And an example, if we spill variable c in this case, then we replace its interval with two micro intervals, one for the definition and another for the use. If we spill, then we add a store right after the definition of a variable following the spill everywhere approach. Once we find any micro interval associated with that variable, we place a load right before it. Stores and loads perform the movement of variables to and from memory. As an example, the program on the right shows the loads and stores that we insert for the program on the left. Following with our example, we have one store at the definition point of variable c, right after its definition, and a load at the use point of variable c, right before the use. C has only one use, thus we only insert one load for it. If it had more uses, then there would be one load for each use. As a consequence of allocating registers, we might end up assigning the same registers to both the variables used in a copy. That's excellent when it happens, because it means that we can remove that copy. It becomes a no-op, moving the contents of a register into itself. This optimization is called coalescing. For instance, in this example, we have a few copies that get coalesced away. The four first copies are coalesced. Linear scan itself does not do much to try to maximize the amount of coalescing, but coalescing naturally happens as a consequence of linear scan. It's common that a copy links the end of an interval with the beginning of another interval. We can simply reuse the register in this case, provided that those intervals don't really overlap. We can augment the core algorithm slightly so that we explicitly try to assign intervals to copies to the same register. You can see the extension in this figure. I suggest you to stop the video and read the code again. Before we finish the class, let's just revisit an important observation. I said in the beginning of this class that linear scan is not optimal. Indeed, it's pretty far from optimal. However, interval graphs can be colored optimally in polynomial time. So where's the inconsistency? The thing is that the intervals are a poor model for the problem of register allocation. That's a poor model because live ranges have holds, whereas the intervals are contiguous. For instance, consider this program on the right. That's the same program, this time with the live ranges of the variables. I've split instructions, so there is, in a way, one basic block per instruction. Notice that we can easily compile this program with two registers. However, any linearization of this program would force us to use three registers. The thing is that with the intervals, depending on how we lay out the basic blocks, we cannot model the fact that variable x and b are not alive together. And this example closes our class on linear scan. This algorithm, linear scan, is very fast and is typically used in the context of just-in-time compilers, where compilation time is an issue. In the next class, we shall talk about another way to deal with register allocation, the graph coloring approach. Graph coloring-based algorithms are slower than linear scan, but typically yield much better code.